Hello, everyone. My name's David Becker. I'm an architect for GPU clusters at OCI. I was going to be speaking here today with my friend Jack Brar, but he's a little under the weather and wasn't able to travel down there. No big deal, he'll be fine. So I'm here today to talk to you about how we've developed our RDMA networks at OCI. When we first launched the product, we targeted our initial use case of HPC compute. And we were determined that we would be large scale. We had designed a system that would run at 1,000 nodes, and that would be able to run our HPC jobs for customers. As you can see on the monitor here, we had a sponsorship with the F1 team, Red Bull Racing, and this is a two-way deal. They also are collaborators with us and run some of their computational fluid dynamic jobs on these clusters. Now, 1,000 nodes is way more necessary to run one simulation, but it can run lots of simulations. We've had a history of continually underestimating how big clusters need to be and what the demand was. But as time's gone by, we've grown and grown, and now we are running hundreds of megawatts at a time. And these networks have to scale to 100,000 nodes. So we've had to grow 100 times. We have AI megafactories around the world. We have them from Utah to Malaysia. This is a picture of our site in Abilene, where we're building a huge network to work with OpenAI. And we have to have networks, RDMA networks, that cover 100,000 nodes. Now, we're a latecomer to the cloud. We're a second adopter. Most of us were refugees from other hyperscalers. We learned a bunch of mistakes there, went to start OCI. We didn't repeat the mistakes we made before, but we got to make brand new mistakes. But we're doing great. The Gartner Magic Quadrant rates hyperscalers, and we're up in the upper right-hand corner with the other major hyperscalers and doing great. We're around the world, got a global network. We started in 2016. That's when we launched our first region. Then in 2018, we had our RDMA network go general availability. We have customers from the automotive to do the HPC works. Fiat Chrysler America was one of our first big HPC customers. We've even had high-frequency trading on our network. And this was because we had a real attention to the latency that we could do. So just to level set for everybody, this is an RDMA network. RDMA stands for Remote Direct Memory Access. RDMA is a little offload engine that lives in the NICs. It can directly copy memory from one server to the memory of another server if both NICs at both ends are running these RDMA engines. This is very efficient and very low latency because the CPUs or the GPUs these days are not directly involved in moving every bit. It's all offloaded onto these RDMA engines. When we first started, like I said, we had clusters of 1,000 nodes, and that was enormous at the time. It was like, how many customers do we need to fill 1,000 nodes? But we soon were doing designs that had 2,000 nodes, and then we needed to get 16,000 nodes, 64,000 NICs, and nowadays we're doing designs with 100,000 NICs in them. So, you want to build an RDMA network in the cloud. You have two big problems. One is latency, and the other is multi-tenancy. Our cloud data centers are huge. If you heard some other people talk about, the distances involved can be very large. Traditional customers that use the cloud have nodes or VMs scattered all through the data center, and the latency is involved to connect those nodes going through multiple layers of the network and through very long cables. Inside the single building can be 300, 400, 500 meters. That's a lot of latency. The solution that we used for our 1,000 node cluster was fence off, in essence, a small section of the data center, take a couple rows and say, this is where our RDMA network is going to be. And since we physically isolated it to that part of the data center, that means that we had great latency benefits there. Those rows had the regular network to talk to the internet and everything else that they need to talk to, and they had a backend network that did the RDMA communication within those two rows. So how did we do? ETH Zurich did a paper in 2022 in Sigmetrics. They analyzed the 4 big hyperscalers, including us, and 3 different supercomputers. And these graphs here show the results. The slopey lines on the right show bandwidth that was achieved, and the inset graph on the left shows latency. So this was Jag's favorite slide. He wanted the audience to guess which line was Oracle. The answer is the red line with the pluses. So for the bandwidth slope line there, we're at the highest bandwidth for every message size for RDMA messages. On the latency side, we're down there at the bottom. There is one supercomputer that's below us. We're tied with another of the supercomputers, and the hyperscalers have latencies that are higher. So our RDMA network is built on RoCE. RoCE stands for RDMA over Converged Ethernet. The original RDMA was built on InfiniBand. And back 10 years ago when we were trying to build this, there are problems with that. We really wanted to use Ethernet. That's multi-vendor. We can get supplies and the latest technology from lots of different people, and that's a huge advantage. Also, InfiniBand didn't deal well with multi-tenancy. And in the hyperscale cloud, we have a lot of tenants. So that's an absolutely deal breaker if we can't do multi-tenancy. Things has changed over the years, but when we were building this originally, that was the constraint. So another factor that helped us do our cloud is that we run on bare metal. Okay, not a heavy metal bear, this kind of bare metal. So when Oracle first launched OCI back in 2016, we launched our initial cloud with bare metal machines. And this was a defining characteristic of OCI. We were very proud of our bare metal. And from this picture here, you can say what a GPU bare metal cartoon kind of looks like. It still has a front-side network, but it has a bump in the wire that's outside of the box to do all the virtual networking that you normally have in if you had a VM running in the data center. The bare metal host allows customers to do anything they want to it. They can reboot it whenever they want. They have direct access to all the hardware. There's no hypervisor in the way causing any kind of latency issues. They can even change the firmware if they want to. If they want to upgrade the NICs to the latest firmware, they can do that because they have full access to the bare metal. This is a diagram of a H100 host. So H100 hosts have 8 GPUs in it. Each GPU would have one CX7 NIC paired with it, and then all those NICs connect to the cluster network. And since each host has 8 connections to the cluster network, we need a large cluster network to connect everything. Large was the opposite of latency. As like I said earlier, we got low latency by having a really small area of the data center. Now we need cluster networks that cover the entire data center. So now we're back to our latency problems. Turns out, though, that the big AI users that want to train their large language models tend to send very large messages. The messages can take, say, 500 microseconds to send. If we go from our single-digit microsecond latencies, which we're so proud of, to 10 microseconds or 20 microseconds more, and your message completion time goes from 500 to 510 microseconds, they don't care. As long as they can get the message, the scale that they need, the little bit of extra latency isn't a factor for them. We still support our low latency products, but we don't put our databases, Exadata database, or the HPC on the very large fabrics. Those are exclusively for GPU use cases. And that means those fabrics can get to be measured in megawatts, like the previous speaker was saying. When we first started, we did a 2-tier network. Leaf and spine, it's commonly seen around. These are called CLO network, or technically a folded CLO. The property of these networks is that they can connect the number of NICs proportional to the square of the number of ports on the front of a switch. That's called the radix of a switch. So if you have a 64 port switch, your radix is 64, and you can do the math and figure out how much you can get. So we could have, with a 64 port switch, get this size topology to go to 2,000 nodes. When we first started, we did 1,000 nodes, and that's because we had different port counts at the different layers, and we chose switches based on what our target size was going to be. As things grew over the years, we went, as I said, from 2,000 nodes to 16,000 nodes, and that couldn't be handled just by increasing the radix of the switch. We had to add a layer to the network. This is what our three-tier network looks like. So we added a superspine at the top. The two large boxes at the bottom still represent the two-tier network like I was just showing previously. The difference is that the spines in those blocks, as we call them, have half of their ports facing the superspines on top. So the proportion, it's still n squared inside each block, but the proportionality isn't quite as large because of that. That means that we can scale this now to a factor that's proportional to the cube of the radix of the switch. So we could have, if you have 64 radix port switches at the superspine, you can connect 64 blocks. This allows us to get up to 64,000 nodes, which is pretty big. And then to get even larger, we'll use larger radix switches. And we have designs now that we're talking about using the Tomahawk 5 with 512 ports. We're probably not going to do 512 cubed. All right, so I'll tell you a little bit more about our properties of our RDMA network. First is that we have full bisection bandwidth. This is a bit unusual. We did splash out, if you will, to make sure that we got full bisection bandwidth. This means that every NIC in the network can send at full speed, and there is a unused path within the network to connect to its destination. This is very helpful in combating congestion. We also give the network presentation to the customer as a VLAN. When we started off with a 1,000 node network, saying here's a VLAN with 1,000 nodes on it, worked great. 2,000 nodes, worked great. Then we grew to 16,000 nodes. Didn't work so great. I mean, we got it to work, but you have to tune Linux to be able to handle a single VLAN with 16,000 nodes on it. In the future, we're changing to use layer 3. We'll be using IPv6. So the customers will see a IPv6 subnet that only has their nodes on it, and they can only talk to the other IPv6 addresses within that. We also have multiple QoS queues so that customers can choose what the behavior is of their traffic going through it. We have some slides later that will explain that. A few more properties of our network. Like I said earlier, we have multi-tenancy with .1x. It's IEEE 802.1.1x to log in. We give each customer a certificate, an X509 certificate that's unique to that customer, and they use that to log into the switch that a NIC is connected to. When the switch gets that login, it configures that port to only allow traffic for that particular tenant to either go into that port or out of that port. And this guarantees that all of our customers are isolated from each other. This is critical. The reason we could go with that is that the scale of users on a particular RDMA network island isn't in the millions. Our front-end network has virtual networking that can handle millions of customers. The problem is that solution has a fair bit of latency to it. The .1x solution doesn't have any latency. You have direct access to the network. Now, let me talk a little bit about congestion control, because this is a big issue for our performance. We do not use end-to-end PFC. As previous speakers have said, you can have head-of-line blocking problems, and in a multi-tenant network, you have multiple tenants sending PFCs, that's a no-go. But we do use it in a limited fashion. we have PFCs enabled from NICs to TORs, which is an interesting case. What it means is that sometimes the RDMA engines on these NICs cannot actually keep up with a complex set of flows coming into it. And they can't take line rate, but it really helps the performance if they can tell the NIC to briefly stop the flow and queue up packets in the TOR, briefly stop the packets going to that NIC. So that is something that we do use PFC for. The other main congestion control feature that is supplied by our network is ECNs, explicit congestion notification. This is a feature of TCP/IP. You can set a bit in the IP header that says a packet has encountered congestion. So if a packet hits a queue that has passed certain thresholds, the switch will set a bit on that packet saying that it hit some congestion. That packet will go on to its final destination. The RDMA engine there will see that that bit is set. It will send a congestion notification packet back to the source. That source NIC will receive that CMP packet and tell DCQCN, which is the congestion control algorithm, that congestion has been seen. DCQCN will do some rate limiting and back off that flow. So customers can choose what the ECN settings will look like. We have a couple different classes of service. For the HPC workloads, you want the best latency possible. That means at the first hint of congestion, we start marking every packet saying there's been congestion, there's congestion. At the other extreme, the workloads for machine learning are pretty tolerant and actually prefer to have some queuing happen so they don't have to do any retransmits or back off. So there we have the queue threshold set pretty high. All this threshold setting is going back and forth with DCQCN, tuning on that side, tuning on this side, and we work closely with our customers to tune it to get maximum performance. We have run into some challenges building networks at this scale. One of them is link flaps. Running these networks on the latest, greatest optical technology, these days 800 gig and previous generation 400 gig links, our clouds and other clouds have seen that they will occasionally flap for no particular reason. If you follow the standards, if you get a burst of uncorrectable errors on the link, the switch is supposed to take the link down and renegotiate the link. We worked with our vendor to get a debounce system so that it'll say, well, okay, I'll just ignore those errors. Those packets are dead, they're dropped, they have to be retransmitted, but instead of renegotiating the link, it'll keep the link up. And if the link goes down, that can and has killed these training jobs. If you're running a training job for weeks at a time, over tens of thousands of GPUs, you do not want your job to die. Another challenge that we've encountered is congestion, where despite all our efforts, two flows get mapped onto the same link, say going from a leaf to a spine. We've developed with our vendors collective load balancing. This is where the switch actually peaks at the packets. Collective is a fancy name for our RDMA operation. And when it sees, the switch sees that a new RDMA operation has started, it will assign that to known port. So it knows what ports it's assigned collectives to. And as long as these collectives have multiple QPs, I won't go into that detail, but as long as there's multiple QPs, there's always a slot for that flow to be assigned on the uplinks, avoiding congestion. So there's a few things that we're hoping will develop in there for our future networking. And first is interoperability between RDMA NICs. Our RDMA clusters right now have to have the exact same NIC in the entire cluster. So it's all CX7. And that's because only CX7s can talk to the RDMA engines and CX7s. The Ultra Ethernet Consortium is making a new standard that hopefully will allow vendors to create some more interop on Ethernet. That would be awesome. Ultra Ethernet also has some packet spraying ideas, and this will be very useful for the congestion control problems that I talked about. We're also working with vendors on the link flap issue that I was talking about. The link flaps can be tackled at all levels of the layer 1 network. We are talking to many vendors and some startups on ways to create something that's just as reliable as that good old Cat5 cable. So that's how we do RDMA at scale, how we went from 1,000 nodes to 100,000 node networks. Thank you very much.